All right, we're going to talk today about a few applications of double integrals. As I've said, the reason why calculus is so powerful is because any time you can set up something as a sum, you can then treat it as an integral. So this section goes into a lot of applications, and I'm not going to do all of them. I'm going to do a few basic ones, and you can read more if you want to. So, first thing is density. So we know the formula is mass is density times volume. Well, what if the density is changing? Well, then the way to do that would be to integrate density across volume or area or whatever and get mass. My notation will shift a little, use rho for the density function, but I heard originally that in two-dimensional you're supposed to use sigma for density, so honestly you can call it whatever you want, and I don't really care. But, yeah, we're going to have an integral of, let's say, charge density. So you've got a metal plate that is a triangle with these vertices, and the charge is somehow artificially distributed so that xy is the density. And we're going to try to find the total charge. That's a little ugly. Let me straighten that out a bit. It's not much straighter, but oh well, close enough. All right. 0, 1, 1, 1, 1, 0. Now what we have here is an example of a continuous distribution. You see, you couldn't really pick a single point and say how much charge is at that point, because the point is infinitesimally small. A single point contains nothing. But you can come up with a representation of the density, in this case xy, and you can use that with an integral to get the total charge, or the charge over any subsection. And this gets into measure theory, and it's very, well, it's complicated, but basically it's saying that if we have any region, we can integrate this function over that region to get the total charge in that region. But it doesn't mean anything if it's just a single point or a line segment with no width. So, I'll say, well, what is this? Well, this is y equals negative x plus 1 along that branch there, that side. So we have a double integral. If we want to integrate over this region, the double integral of xy dy dx, where y goes from negative x plus 1 up to 1. X goes from 0 to 1. Again, the first integral will have variables in it. The second one will have only constants, or whatever the last one is. In this case, there are 2, so that's the last one. So we go 0 to 1. We say y is negative x plus 1. Y equals 1. Integral of y would be x over 2y squared dx. See, the x is a constant. Integral of y is y squared over 2, and I just move the 2 over to the x just because I think I'll make the calculation a little easier to work. So then that becomes 0 to 1 of x over 2 bracket 1 squared minus negative x plus 1 squared dx. Do your algebra. That reduces down to, let's pull the 1/2 out, 0 to 1 of negative x cubed plus 2x squared dx, which then becomes 1/2 0 to 1 of negative x fourth over 4 plus 2/3 x to the third is 1/2 negative 1/4 plus 2/3 is 1/2 times negative 3 over 12 plus 8 over 12. So that's 5 over 12 here times 1/2 is 5 over 24. I guess the units were coulombs. And density would be given in coulombs per meter squared. So then you'd integrate. Integrating is a form of multiplication. We have, here's units are coulombs per meter squared. And this is times meter again, so the meters cancel out. On a test, I might give you a problem like this. Find the total volume or total mass. Sorry. In this case, it was charge density. It could just easily be mass density, regular density, and it would be kilograms per meter squared instead of coulombs per meter squared. So I might ask you to find this on a test, but I don't think, I'll just say it. Nothing else in this section will be on a test. However, it is on the homework, so I'm going to go over them anyway. But the reason why I say that is because some of these applications, the formulas are long, they're complicated, and they're hard to remember, and so I'm not going to put them on there. All right. Next we want to talk about is center of mass. And mostly what we're going to be doing here is just learning new setups. And once we have the setups, then the integral process is the same as every other. So let's talk about how center of mass works. So let's say we had a bar here. It's uniform width. Its density is going to be lambda kilograms per meter, meaning every meter along here, the density is given by, we'd integrate to get the mass. So the density is a function lambda. It's linear, so L, linear, L for lambda, as opposed to sigma for square, I guess. The idea being a metal rod, technically there would have to be a depth and a width to it, but we're saying that as we go along the length of it, lambda gives the density, and the width and the depth are the same the whole way. So we don't really need to think about them. So let's say we put some weights on here. We'll call this point 0. And we'll put some weights here. Little pin prick here. It's pointing down. They're glued on here and they're pushing downward. And we want to know what's the center of mass. And what does that mean? Well, it means there's one point where it all balances. And if you were to put a support under that point, let's say it was over here, for instance, then as long as it was sturdy enough to hold it, you could balance the whole thing right there. So how do we find that? Well, it's essentially a matter of looking at the torque here. See, each one of these has a distance, we'll call it, or a position xi. So these would be negative values for xi. These would be maybe I plus 1, however you want to label them. I plus 2, I plus 3, etc. And this would be, the mass would be mi plus 1, etc. And so the torque would be proportional to the mass times the distance. Torque is force times distance. Force is proportional to mass since gravity is the only force acting on this. So we could find the center of mass like this. We would say we will sum up all of the mi xi and then divide by the total mass. And that would give a location. See, the MI, XI, we multiply them out, and it gives us all the torques and the net torque. But the units are wrong because we just want a position, not kilograms times meter, whatever a kilogram meter is. A joule, I guess? No, that's not right. I don't know what that is. But point is, we don't want kilograms in our final answer, so we divide out the total mass. And so this, well, we'd say, we could rewrite this. The MI, what is the mass of an individual weight? Well, if we have this function lambda that gives us the mass, or that gives us the density, then it would be lambda times delta. Let me back up a little. on that. Sorry, I got a little ahead of myself. So that's the formula if there's a discrete number of weights. But what if the bar itself is weighted? We generally ignore the weight of the bar, but what if we don't? Well, obviously we just have a bar. But it's not uniform density. Different parts are heavier than other parts. So what do? Well, we divide the bar up into lots of little sections, just calculation-wise. This is just Riemann sum method. The width of each one would be delta x. And the position, this time we'll call this 0, and we'll go over here. The distance along any point would be x. X, x1, x2, x3 if you like. So, what is the mass of one of these bars? Let's not even call it MI, since we'll call it delta M. Well, it would be the density, lambda, times the width, delta x. In fact, let's even write this as a function. This is delta of x. Lambda of x times delta x, meaning the density at a point. We're sort of, as usual, we are assuming we're picking a sample point in here, plugging that in to get the density, and then assuming that's the density for the whole section, multiply it by the width, that would give us the mass. So this is just another application of Riemann sums. And see, this is one of the things that this modeling is useful for. Actually solving these is, honestly, these days is a lot of it's done by computers, but knowing that you can split something up into a sum and then turn it into an integral is a skill that, as of now, only humans can do. So, mi will replace with delta m would be lambda. No, sorry, won't do that. Let's go ahead and change this into an integral. Because we're going to take limit delta x goes to 0. I'm sorry, I'm getting ahead of I get a little mixed up with these myself. If we got finitely many, we'll say sigma of lambda of x times delta x divided by m. And then we will take limit as delta x goes to 0 as we make these divisions very, very narrow. And the function becomes an integral, 1 over m, because little m is a constant, integral of lambda of x. Sorry, I missed something here. This other x we should have carried over. My mistake. Delta x is the width, but we also need to multiply by the position along there. So it becomes lambda x times x dx. So that's how you would find the center of mass on a bar. Now what happens if it's not a bar, if it's some oddly shaped stage? Well, the idea is similar. You would divide it up into a bunch of horizontal bars. And you could say, and I'm not going to work all the way through this because I think it would get too complicated, but it's in the book if you want to see it in more detail. But you could say, well, I need to know what the position along here, the y bar, is, and position along here, the x bar, and then the intersection would be the center of mass. So you would divide it up vertically into pieces, and you would do that same center of mass calculation, and then you divide up horizontally, you would do the center of mass calculation, and that's how you would find it. So let's go ahead and skip to the formula here. We get mx is the double integral of y sigma of xy dA across the region D. Again, this is the moment about x. And I will be honest, this is the part where I kind of have trouble explaining it, because this is really more of a physics type thing than a pure math thing. So explaining what exactly a moment is, I find that a little tricky. It is something to do with different weights and different characteristics of the distribution. But that's about the best I can do right now. My will be the double integral of x sigma xy dA. So notice how they don't match moment about about y-axis. So the my you integrate by you multiply by x first. The mx you integrate with multiplying by y first, because it's saying how far away are you from the x-axis. Well, y is your distance from the x-axis, so that's what you're multiplying by. This is not the center of mass, because again we have to divide out the full mass. So x bar is my over little m. Y bar is mx over little m. And so the center of mass is x bar comma y bar. All right, let's go ahead and do an example of this. So, like I said, I don't want you to worry too much if you don't understand the whole construction and everything I did there. I just was trying to set it up and give you the idea. But if you can do it with the formula in front of you, then that's okay for now. If you are, into physical engineering and such, you might need to eventually get a better, more intuitive understanding of how center of mass works. But for this class, it doesn't need to be all that deep. You just need the basics here. So let's find the total mass and center of mass of a triangular lamina with vertices 0, 0, 1, 0, and 0, 2. Density function is this. Lamina, by the way, similar to lamination. It means it's a triangular region. The depth of it is negligible. It's pretty small. You can think of it as like a centimeter or something small like that. But it's the same everywhere, and so the top is not different than the bottom. Yeah, it basically just means that we can ignore the depth. We can treat it like just a piece of paper or plastic. Okay, so all right, 1, 0, 0, 2, 0, 0. Okay, and we have a density function sigma of xy is 1 plus 3x plus y. That's it. So we need to integrate across this triangle. Y equals negative 2x plus 2. Now, in our formula, and you can go back and I hope you copy down those formulas, but I have them in front of me, so I'm just going to be referring to them because I haven't memorized them. But our formula says we get the center of mass by getting the moments and dividing by the total mass. So it might make sense to start by getting the total mass. Well, the total mass will be the double integral across this triangle. dy dx, so y will go from 0 to negative 2x plus 2 because I'm choosing to go vertically. You could go horizontally if you wanted. You just have to solve this for x. This is both type 1 and type 2. Use whichever one you prefer. X then goes from 0 to 1. So then we do the integral. We get integral from 0 to 1. Integral from y is 0 to y is negative 2x plus 2. Y plus 3xy plus y squared over 2 dx, which becomes 0 to 1 of negative 2x plus 2 plus 3x negative 2x plus 2 plus 1/2 negative 2x plus 2 squared dx. Do your algebra, ... I'm going to skip a lot of this. We get 0 to 1 of negative 4x squared plus 4 dx, which then is 0 to 1 of negative 4/3 x to the third plus 4x, which is negative 4/3 plus 4, or 8/3. Okay, so that's the mass, is 8 over 3. And so you would copy that down because you'll need it for the next part of the problem. And at this point, I'm just going to set up. The problem is worked out in full in the textbook. These examples I'm doing are straight from the textbooks, so you feel free to look over them if you would like to, if you don't follow all the details. But I'm going to show the setup. So x bar was defined as my over m, which is further defined as 1 over m. Again, the little m is a constant with respect to x and y. It's the mass of the whole thing, so you can pull it out of the integral. Double integral of my means we have to multiply by x. So it's x sigma xy dA across the region. So if we plug in our specific values, m is 8/3, so 1 over m is 3 over 8. Double integral of x. Let's just multiply this sigma up here by x. X plus 3x squared plus xy dy dx, where again y would go from 0 to negative 2x plus 2, and x would go from 0 to 1. And so I'm not going to work this one out. It comes out to 3 over 8. If you want to test yourself, you could try it right now and see if you get the same thing. And then for y bar, well, we'd see mx over m, which would become the double integral of, 3/8 here as well. And same thing, 0 to negative 2x plus 2, 0 to 1, but instead we're going to multiply by y this time. So we get y plus 3xy plus y squared dy dx, which ultimately gives 11 over 16. So the center of mass is 3 over 8, comma 11 over 16. So you go out to about here, 3/8, and up to maybe here. Something like that is the balancing point. It looks like it shouldn't be that high up, but remember, our distribution, our density is not uniform. The top, since it's with y, and also the right from x, are going to be heavier. Larger x, larger y means more density. So this right edge is heavier than this piece down here, even if they're the same length. Even a little piece here, a little piece here, the one on the right will be much heavier than the one on the left bottom. So that's why the center of mass is probably farther up than you might have expected, and a little farther right too. Okay, what else we got? What's next? All right. So, proportional density. Suppose the density at any point on a semicircular lamina is proportional to the distance from the center of the circle. Find the center of mass. Okay. What does that mean? Well, let's draw our semicircular lamina first. So that means something like this. So it's like a sort of a, maybe think of it as like a stage, like where you're giving a presentation on a semicircular stage. And you want to know where it's balanced because you have to build supports on the stage so it doesn't collapse. Now it says it's proportional to distance. So any point, it'll be, you'd say how far away is it, and that would give you a formula for distance. That means, well, distance is r. This makes most sense with polar coordinates. We say it's proportional distance, we're saying it's equal to k times r, where k is some constant. Yeah, proportional to distance just means that the density is always the same as the radius times a constant, for the same constant for the whole thing. So, we can work out different parts. Now, for starters, I think it's clear that x bar is 0. Now, you could calculate this if you wanted to, but since this thing is based only on distance, that means the left side and the right side are perfectly symmetric, and so they'll give the same value and cancel each other out. The y bar is a little different. So let's say, okay, y bar will be somewhere along this line. It'll be 1 over m double integral, we'll call this region D, double integral across D of y k r dA. Okay, that's ugly. We can't have both y's and r's in the same integral. So we're going to need to convert this y into polar coordinates. So this becomes, let's pull the k out, k over m, and I'll deal with the m later. Or you could do it first, but I'm just going to do this way. Double integral of r sine theta times r times dA would become r dr d theta. Remember that extra r that comes when you switch to polar? I forgot it myself when I was working on the notes. Okay, so this can now factor as, oh, and what are the bounds? Well, r, I'm going to call the radius here big R. The book calls it A. I prefer using big R to emphasize it's the largest radius. So little r is a variable. Big R is the largest that little r ever gets. So little r would go from 0 to big R, and theta would go from 0 to pi. This becomes k over m, and then we'll split this up. Integral from 0 to pi of sine theta d theta. Integral from 0 to big R of r to the third dr. That becomes k over m, 0 to pi of negative cosine theta, 0 to r of r to the 4th over 4. Then we get k over m. And then we plug in pi to negative cosine. Cosine of pi is -1, so it becomes 1 minus. Plug in 0 to negative cosine becomes -1. Times capital R to the 4th over 4. So this becomes, this is 2 over 4, reduces to 1/2, so we get k r to the 4th over 2m. All right, so that is our y bar. We just need to work out what m is. So that means we just need to integrate the density function. So copy all this down, and I will erase. Used to be able to scroll this thing. I think an update means I can't do that anymore. Or maybe I just don't know how. I just accidentally turned it off. And anyway, let's do the double integral of kr across the whole thing. So r dr d theta where, again, r goes from 0 to big R, theta goes from 0 to pi, is 0 to pi d theta. I'll pull the k out. K is just a constant. It depends on how this stage or whatever is constructed. It's not a mathematical fact. It's just we'd have to, get out a measuring something. We have to get some tools to measure it. R squared dr. So that would become k 0 to pi of theta, 0 to r of r cubed over 3. Yeah, when it's just d theta, you could just write as pi minus 0 and be done with it, but I'm working it out anyway. So we get k pi r cubed over 3. So that's m. So then we need to plug it into this function here. So it would be k r fourth over 2 k pi r cubed over 3. Let's see, we can flip that 3 up to the top. And then a lot of stuff divides out. 4 of those r's divided all 3 of those r's. The k and the k divide out, meaning that being proportional, it doesn't matter what the proportion is, it won't matter in the end. So we get 3r over 2 pi. I'd prefer to factor out the r, 3 over 2 pi times r, because then visually I can say, well, 3 over 2 pi is a little less than a half, so I'd go up almost halfway. And that would be my center of mass. Okay, we're almost done. This is going to be a short one, partly because I'm skipping most of this moment of inertia problem. It's really long, and I don't feel like dealing with it. Moment of inertia, Ix is y squared times rho xy, or sigma xy, the density. Moment of inertia for y would be x squared times that. Moment of inertia about the origin would be the distance, which is x squared plus y squared, times the density. What do these mean? Well, essentially they represent how hard it is to rotate something about the axis. Inertia, in physics terms, inertia is resistance to force. And so normally that's mass. Mass and inertia are kind of the same, but we're talking about rotation, they're not the same. So if we say we have a big disk here, we want to spin it about the y-axis. So we'd have to push it in some way. I'm pushing into the page here. would cause it to spin about the y-axis, Ix is basically how hard that is to do. And Iy would be how hard it would be to make it spin about this y-axis, which means I have to push downward into the page in such a way that would make it rotate. I-O would be how hard it is to make it rotate around about the origin like this. So, like I said, moment of inertia is just so complicated that I don't want to spend a lot of time on it. But there's one question in the homework. It says, would it be harder to rotate it vertically or horizontally, something like that. And that basically just means is Ix or Iy the larger value. Whichever one's larger, that is the harder one to do. So larger Ix means it's harder to rotate about the x-axis. Larger Iy means it's harder to rotate about the y-axis. And so it's just a matter of working out this long formula here, which is just a double integral, but with an extra x squared or y squared. So, yeah, like I said, moment of inertia will not be on any test I give. Neither will center of mass. I'm pretty sure they won't give it on the exam either. Something like this, just finding the total mass, that I might put on a test, because it's not too complicated a formula. You don't need to memorize any special formula for it. Now I give you the density. Last application that I want to talk about is probability. So if you take a probability course, you can get what's called a random variable, which is not a great name. What it really means is describe an event that might happen. You plug in the event, and out comes the probability of that happening. So for like flipping a coin, if you plug in what's the probability of a head is 1/2, probability of tails is 1/2. There are two main rules that if you integrate across the entire thing, you get 1. And then there's expected value, or mean, is the same as the first moment earlier, the x times f of x. And if we have two distributions that are independent, then we can say what's the probability of the first one being something and the second one being something else. And if they're discrete, like heads on the first coin and tails on the second coin, you can just find each one and multiply. But if they're continuous, well, we have to integrate over it. So, see an example here. This is also one that I might see on a test because, again, it's not as complicated as the moment of inertia. So, given f of xy is c, x plus 2y, where x goes from 0 to 10, y also goes from 0 to 10, f of xy is 0 elsewhere, meaning we are essentially restricting a domain so that it only has positive values on this square. Find c and find the probability of x is less or equal to 7 and y is greater than or equal to 2. Okay, well, let's see how that works. Delete. Okay, so we go from 0 to 10 of the function, the density function, probability density, x plus 2y, dx, dy, or dy, dx. It's constant, so it doesn't matter. So what we're saying is that the function is only meaningfully defined on this box. And we know then, if we integrate across that, it will give us 1. So if I divide out this c here, well, I'll save that till the end. So let's integrate this left side here. 0 to 10, and x is 0, x is 10 of c, x squared over 2 plus 2xy dy is 0 to 10 of c, 10 squared is 100, over 2 is 50, plus 20y dy, which is, pull the c out, 0 to 10 of 50y plus 10y squared Plug in 10, we get C times 500 plus 1,000 is 1,500 C. We also said it's equal to 1. This is just a matter of rescaling that when people came up with probability, they said the total should always be 1. So that means C must be 1 over 1,500, because that's the only way to make the total integral be 1. Okay, so we've got C is 1 over 1,500. So I can rewrite this density function as, undo that part. I'll take the C, I'll erase it, I'll put it out front as 1 over 1,500. All right, so we are asked, what is the probability that x is less or equal to 7 and y is greater than or equal to 2? So that means here's x is 7. Here's y equals 2. So that means we need to be in this part. And so if the probability was the same everywhere, we would just get the area of this. Since it's not the same, we have to integrate over that. So x goes from 0 to 7, y goes from 2 to 10. So then we get 1 over 1,500. It does not equal 1 anymore. We can erase that because we're not doing the whole integral. We're only doing a part of it. 0 to 2. X is 0 to x is 7. This part's pretty much the same. It's just different limits. X squared over 2 plus 2xy dy is 1 over 1,500. 0 to 2 of plug in 7, 49 over 2 plus 14y dy. So then become 1 over 1,500. 0 to 2 of 49 halves y plus 7y squared is 1 over 1,500. Let me just plug in 2. 49 plus... wait, hold on. Back up. Most of this is right. I just wrote 0 to 2 instead of 2 to 10. That's my mistake. 2 to 10. 2 to 10. 49 over 2. So 2 to 10 of 49 over 2y plus 7y squared equals 1 over 1,500 bracket 490 over 2 plus 7 times 10 squared would be 100, so 700, minus, plug in 2, 49 plus 28, which ends up as 868 over 1,500, which is about 0.5787. Okay, so I hope that gives you a view of a few basic applications. And like I said, don't stress out too much over this section. It could go a lot deeper if we wanted to, but I really just want to get a few basic applications that you can appreciate. All right.